Now we will invite Dr. Dulal Chakrabarti for his talk. So, a simple multilinear convolutional neural network model. So, please, Dr. Chakrabarti, yeah, please.
Can you hear my voice?
Yeah, I can hear your voice, but there are no presentations. Please present your, yeah.
Okay, just 1 minute. The screen is visible.
No.
1 minute.
Your screen is visible. Yeah, now fine. Yeah, please. No, again. Start your presentations first on your screen, then it will say.
Is it visible now?
Yeah, it is visible. Fine.
Okay. Thank you, Mr. Chairman, and good afternoon to all of you and distinguished delegates. I present a simple multi-layer convolution neural network model for classification of clouds from Insat cloud imageries. My objective is to build this model using Python and Microsoft Cognitive Toolkit, which is an open source package. Data for this model is collected over the surface observation network of IMD, which is shown here with the cropped image segments superimposed. You can see the inset where I have shown a magnified view of the image segment over port where observatory. CNTK, which is the brief form of Microsoft Cognitive Toolkit, data is processed in the form of text files. As you can see down below the slide, labels are on the left, which is a vector of length 4, indicating one of the low, medium, high, or no cloud conditions, or no cloud types. And on the right are features, which is a tuple of 6 by 9 by 9 pixel integer values. 6 means that is the number of channels, and 9 by 9 is the width and height of the image. Model processing involves downloading of the image data from 3DR and 3D satellites at 6 UTC plus minus 15 minutes, and also surface observational data of 6 UTC. Pre-processing includes georeferencing of all the images and decoding of the cloud groups. Out of this image as well as the observational data, we create a CNTK data frame, extracting image values as well as the observed cloud type. Many such CNTK data frames constitute what we call the data set, which feeds the model with 3 convolution layers in our case. And once the model is trained with the data set, we use the weights and biases of that model to predict the unknown cloud class type. Core concept in the CNN model is the convolution operation. We define here 2 containers, X image values of 6 by 9 by 9 dimension, and Y, the output vector of length 4. Convolution involves scanning by filters of the images, performing the dot product operation between the image and the input values. And bias is added to this dot product. And the sum of these two is optionally mapped through a nonlinear activation function to give the output of this layer, which becomes input for the next layer. Many such layers stacked in tandem produces the final output. And this is the concept of the deep learning architecture. CNN model is built with configurable hyperparameters. An instance of that model is created, in our case, with 3 convolution layers of 8, 32, and 128 filters, with ReLU as the nonlinear activation function. These are followed by a dropout layer with 20% node dropout to prevent overfitting, and a dense layer which fully connects to the 4 output classes. We use 8 parameter tensors and 81,244 training parameters. A small set of observations called mini batch is loaded into the model, and then the average error from that set is used to update the model parameters using stochastic gradient descent. When after thousands of operations, the average error does not change significantly, we say that the model is trained. And these trained models, weights and biases are actually used to predict the unknown classes. One important parameter we found in our case is the learning rate, which when is reduced, and it is actually to be optimized for the best result. We use 25 unknown samples of cloud image, and we find that when the model learning rate is reduced from 0.13 to 0.1, the accuracy changed from 60% to 80%. So to conclude, we say that we demonstrated a model, CNN model with 3 layers, which can predict unknown cloud types with reasonable accuracy. Model can be improved by changing feature size, level size, number of convolution layers, and the learning rate. Insat, some applications could be Insat program has more than 30 years of image data, and a grid point cloud climatology can be developed over India and neighborhood with good temporal and spatial separation. And the model, it is of general nature, so it can be used to classify clouds from Doppler weather radar images also. Actually, this type of model can also find application to classify severe weather clouds like storm clouds as well as the heavy rainfall clouds. I acknowledge with thanks the IMD ISRO rapid portal for the Insat images and the WMO information system portal agency for the surface observations. Thank you, Mr. Chairman.
Thank you, sir. It is in its future applications, because gridded data has been generated, as I remember, by Mahakur of Indian Institute of Tropical Meteorology and something like that. So that can be used. Okay. So it is very nice presentation, sir. Thank you, sir. So now